Welcome to the presentation of the paper, A Variational Information Bottleneck-Based Method to Compress Sequential Networks for Human Action Recognition. For action recognition from videos, LSTMs are required to track the temporal information. For end-to-end LSTMs, the input feature vector is of large dimension, here 57,600, for an example taken from UCF11 dataset of 3 channels of 160 x 180 pixels each. The combined LSTM matrices are shown as WVH, which is multiplied to the input vector VT, and WHH multiplied to the hidden state vector HT. The large input dimension and the hidden state lead to millions of LSTM parameters which require hundreds of MBs of space. Similarly, CNN LSTMs whose feature vectors are of size 2048, given by popular extractors such as InceptionNet, ResNet, EfficientNet, along with hidden state dimension of 256 leads to again millions of parameters and many MBs of space. Edge devices require applications to often fit within 1 or 2 MBs. Thus, model compression is required. Our working principle is based on information bottleneck theory introduced by Tishby for DNNs in 2015, which assumes a Markov chain from input to the output layer. This work presents that to get the most prediction-relevant representation, one must maximize the mutual information between the target vector and the hidden layer representations. At the same time, to get the most concise representation, one must minimize the mutual information between consecutive hidden layer representations. We adapt this theory to LSTMs to get the most relevant hidden states required for prediction. The loss function is formulated as given, where k tilde refers to the compressed gate representation given the feature vector v and the class vector y. Since this loss function is intractable, we invoke a variational upper bound which is minimized. The VIB LSTM equations are similar to the usual LSTM equations except that there's a dot product with z vectors whose values are sampled from Gaussian distributions with mean and variance learned from the data. In order to compress end-to-end LSTMs, VIB principle is used to get the most prediction-relevant features and the hidden states. The weights corresponding to the irrelevant features and hidden states are zeroed out, shown by white stripes in the LSTM matrices, which leads to sparse LSTM matrices. These can be compacted to form smaller models. Shown for UCF11 dataset, this leads to 332x compression. Our method compresses both feature input vector and hidden state vector, unlike previous tensor decomposition methods. Thus, our method gives the highest compression ratio along with comparable accuracy. For CNN LSTM architectures, the feature vector extracted needs to be passed through VIB masks and the LSTMs are to be replaced with VIB LSTMs. The whole architecture needs to be trained with the VIB loss function, which leads to sparse LSTM matrices which can be compacted to give smaller models. Our method leads to the highest compression ratio among all for CNN architectures. Combining our method with group lasso compression technique leads to even higher compression ratio but at the cost of lower accuracy. We also note that for same LSTM parameters, VIB LSTM-based architectures give higher accuracy than naive LSTM architectures. But there's a limit to compression with VIB. After a certain number of parameters, the accuracy starts to degrade. We see that for an uncompressed model, on Raspberry Pi it takes 1.26 seconds to infer action from a single video, whereas a compressed model takes just around 13 milliseconds. Thus, there's a 100x speedup. Concluding, this paper presents a generic RNN compression technique based on VIB theory that extracts the prediction-relevant information. The method compresses the whole LSTM architecture, both the input and the hidden dimensions. Loss functions for end-to-end LSTMs and CNN LSTM architectures are formulated, and the approach can effectively be used with other compression methods. The code will soon be publicly available when the paper is published. The references are listed here. Thank you for your patience.